Algebra, like arithmetic, involves numbers on which are performed operations such as addition, multiplication, subtraction, and division. While arithmetic is concerned with operations on specific numbers such as 2 plus 5, 8 times 9, 43 minus 18, 36 divided by 4. In algebra we deal with operations on unspecified or unknown numbers that are designated by symbols or letters such as x, y, z, a, b, and c. Thus in algebra we consider x plus y, a times b, y minus z, b divided by c. The word, algebra, originated from the Arabic word al-jab, which appears in the title Ilm al-Jab wal Muqabala, translated as the science of reduction and cancellation, an early 9th century work. The algebraic symbolism used to generalize the operations of arithmetic was formulated in the 16th and 17th centuries. Before we define real numbers, let us first define a set, because from time to time we will use some set notation and terminology. The idea of set is used extensively in mathematics and is such a basic concept that we will not give a formal definition here. Instead, let us say simply that a set is a collection of objects, and the objects in a set are called the elements of the set. Each particular object must be either in the set or not in the set. A pair of braces is used with words or symbols to describe a set. For example, if S is the set of natural numbers less than 6, we can write set S is the set of 1, 2, 3, 4, 5, or as S is the set of X such that X is a natural number less than 6. In the first notation, we have listed all the elements in the set. In the second notation, called set builder notation, we have given the criteria for deciding whether an object belongs to the set. Here the symbol X is called a variable because it is used to represent any element of the given set. The given set is called the domain of the variable. Another way of writing the set S in set builder notation is to use a vertical bar in place of the words, such that, which is read, the set of all X such that X is a natural number less than 6. Two sets A and B are said to be equal, written A equals B, if and only if A and B have identical elements. For example, the set of 1, 2, 3 is equal to 3, 1, 2. The union of two sets A and B, denoted by this and read as A union B, is the set of elements that are in A, or in B, or both A and B. The intersection of A and B, denoted and read A intersection B, is the set of all elements that are in both A and B. The set that contains no elements is called the empty set and is denoted by. Suppose A equals 2, 4, 6, 8, 10, 12, B equals 1, 4, 9, 16, and C equals 2, 10. Then A union B equals 1, 2, 4, 6, 8, 9, 10, 12, 16. B union C equals 1, 2, 4, 9, 10, 16. A intersection B is equal to 4. B intersection C equals null or empty set. Observe in illustration 1 that the intersection of sets B and C is the empty set. These two sets have no elements in common and they are called disjoint sets. The symbol indicates that a specific element belongs to a set. Hence for the set C of illustration 1 we may write, which is read, 2 is an element of C. The notation indicates that both A and B are elements of S. The symbol is read as not an element of. Therefore we read as, 5 is not an element of A. If every element of a set S is also an element of a set T, then S is a subset of T, written. In illustration 1 every element of C is also an element of A, thus C is a subset of A. And we write. The symbol is read not a subset of. Thus we may write. Now we will talk about real numbers and what it consists of. Natural numbers. The set of natural numbers also called the set of positive integers. Thus the set of natural numbers, which we denote by n, may be written, where the 3 dots are used to indicate that the list goes on and on with no last number. The number 0, denoted by the symbol, is the number having the property that if it is added to any number, the result is that number. The set of numbers whose elements are the natural numbers and 0 is called the set of whole numbers, denoted by Corresponding to each positive integer n there is a negative integer such that if it is added to n, the result is 0. For example, the negative integer, read, -5, is the number which when added to 5 gives a result of 0. The set of negative integers can be written as follows. The set of numbers whose elements are the positive integers, the negative integers, and 0 is called the set of integers, denoted as big letter J, thus J is equal to. The set of integers then is the union of three disjoint subsets, the set of positive integers, the set of negative integers, and the set consisting of the single number 0. Note that the number 0 is an integer, but it is neither positive nor negative. Sometimes we refer to the set of non-negative integers, which is the set consisting of the positive integers and 0 or, equivalently, the set of whole numbers. Similarly, the set of non-positive integers is the set consisting of the negative integers and 0. Consider now the set whose elements are those numbers that can be represented by the quotient of two integers p and q, where q is not 0, that is, the numbers that can be represented symbolically as p over q where q is not 0. This set of numbers is called the set of rational numbers, which is we will denote it as big letter Q. Thus, q is equal to the set of x such that x can be represented by p over q, p is an element of j, q is an element of j, and q is not 0. Some numbers in the set q are 1/2, 3/4, 11 over 5, -2/3 and -31 over 12. Every integer is a rational number because every integer can be represented as the quotient of itself and 1. That is, 8 can be represented by 8 over 1, 0 by 0 over 1, and -15 by -15 over 1. Hence J is a subset of Q. Any rational number can be written as a decimal. You are familiar with the process of using long division to do this. For example, 3 over 10 can be written as 0.3. 9 over 4 can be written 2.25, and can be written 5.1875. These decimals are called terminating decimals because they terminate. There are rational numbers whose decimal representation is non-terminating and repeating. For example, 1/3 has the decimal representation 0.333. Where the digit 3 is repeated, and 47 over 11 can be represented as 4.272727, where the digits 2 and 7 are repeated in that order. The following question now arises: are there numbers whose decimal representation is non-terminating and non-repeating? The answer is yes. One example of such a number is the principal square root of 2, denoted symbolically by, and indicated by a non-terminating non-repeating decimal as 1.41421. Another such number is pi, which is the ratio of the circumference of a circle to its diameter and indicated by a non-terminating non-repeating decimal as 3.14159. The numbers whose decimal representations are non-terminating and non-repeating cannot be expressed as the quotient of two integers and hence are not rational numbers. This set of numbers is called the set of irrational numbers, which we denote by big letter H. It may be defined symbolically as H is equal to the set of X such that the decimal representation of X is non-terminating and non-repeating. The union of the set of rational numbers and the set of irrational numbers is the set of real numbers. Denoting the set of real numbers by big letter R, we define R symbolically by Q union H. This figure illustrates the relationship among the sets discussed. The sets n, j, q, h, and r are the sets of numbers we already defined. Insert either subset or not a subset to make the statement correct. To test your knowledge, answer this exercise. I will reveal the answer in 5 seconds, so pause the video. Solution. In A, because every natural number or positive integer is an integer, n is subset of j. In B, because there are rational numbers that are not integers, q is not a subset of j. In C, square root of 2 and pi are irrational numbers, but 3.5 is a rational number, therefore square root of 2, pi, 3.5 is not a subset of h. In D, 0 is a rational number, and thus 0 is a subset of q. In E, every positive integer is a real number, hence n is a subset of R. In each of the following, determine which one of the sets n, j, q, h, r, an empty set is equal to the given set. A. J union Q is equal to what? B. J intersection Q is equal to what? C. N intersection H is equal to what? D. H union R is equal to what? To test your knowledge, answer this exercise. I will reveal the answer in 5 seconds, so pause the video. Union of J and Q is the set of numbers that are either integers or rational. Because the set of integers is a subset of the set of rational numbers, this union is the set of rational numbers. Hence J union Q is equals to Q. The intersection of J and Q is the set of numbers that are both integers and rational. This intersection is the set of integers, and thus J intersection Q is equal to J, because the set of positive integers and the set of irrational numbers have no elements in common. N intersection H equals empty set. D. The union of H and R is the set of numbers that are either irrational or real. Because the set of irrational numbers is a subset of the set of real numbers, H union R is equal to R.